Today we're going to talk about probabilities and probability theory. Hopefully this will be a bit easier than the previous module. So I'm going to start with some easy problems. So the first problem is this. Suppose that I have a coin and I just keep flipping this coin. What is the probability that I get heads every time, and what is the probability that I get tails? Now, normally you would say that if it's a fair coin, it's 50-50. So 50% of the time I would get heads, 50% of the time I would get tails. But what does that actually mean? It's usually something like this. I would say that I will keep doing the same thing over and over again. And let's say that I do my experiment n times. And let's say that when I do my experiment n times, so I have n experiments. Each experiment is just one coin toss. And let's say that I get h heads. And of course, I will get n minus h, which is t tails results. So what I want to say is that, well, what is the ratio? What is the ratio of heads to the total number of experiments? And I'm especially interested in this when I keep doing this over and over again. Okay. So what happens if I keep tossing coins? So let me show you some simple thing. Let's do a little bit of coding, even though this course doesn't really have coding. So let's say I just write a code that does this for me. So I'm going to have like this. I don't think I need CS to deliver whatever. So this is what I want to do. I want to take some number n as input, and then I want to simulate n coin flips, right? So first I'm going to seed my randomness because, okay, this is again not something that we really care about in this course, but computers cannot create random numbers. So whenever you're using a random function in C++ or any other language, it's actually pseudo-random. It's like a deterministic function that looks kind of random to us. It's not really random. But for the purposes of this course, let's say that it is random. So I'm just going to say for n times, let's do this. Let's say that I take a random number and I take it modulo 2. So with 50% probability, it's going to be 0. And with 50% probability, it's going to be 1. And I'm just going to assign one of them to heads and the other one to tails. So let's say this one is heads and this one is tails. Okay. And let's say I also count the number of heads and tails. So here I will just increase heads. In this case, I will increase tails. And then in the end, I will write the ratio. So I will write h over n. I have to, of course, do something like this. And then the ratio of tails. Okay. Let's say that I want to toss 10 coins. Ooh, what happened here? Oh, I didn't initialize it right. Okay, this was weird. Okay, let's say I do 10 coins. See, 40% of them were heads, 60% were tails. Let's do this again. This time it was 50-50. Let's do it again. Again, 50-50. And now 60-40 in the other direction. Let's have many more coin tosses. And as you see, it's kind of close to 50-50. Not exactly, of course. Now, here's the thing. The problem I have here is that I can do this experiment And I can, of course, count and I can compute the ratio. But if I want to define my probability as something like this, if I want to say the limit as n tends to infinity of the number of hits that I see divided by the total number n of experiments, how do I even know that this limit exists? So of course, I'm doing these experiments and the numbers look kind of similar, right? But how do I know that if I do this experiment for an infinite number of times, these two numbers will both converge to 0.5? Maybe they don't, right? So this is not a good definition for probability. I don't want to work with definitions that are hard to prove existence for. So I want to be able to give a definition of probability such that I don't have to constantly think about, does this probability even exist? Okay. Great. So I'm going to give you a bunch of puzzles first, and then based on these, we will go back and have like an axiomatic way of defining probability spaces. So here's the first puzzle. You've probably heard about this. This was what a famous American game show did. So suppose that we have 3 doors. So I have door 1, door 2, and door 3. And behind one of these doors is a prize. The other 2 doors don't have anything behind them. Okay. So you're playing this game. Let's say I'm the host. I ask you to choose one of the doors. And I've told you that we have put the prize behind one of the doors randomly, and this was a uniform random selection, so the probability of each of them having the prize is exactly 1/3. Okay, so I tell you to choose one of the doors. Let's say in this case you choose door 2, and when you do that, I open another door and show you that that door was empty. So for example, I show you that door 3 was empty. I can always do this because only one of the 3 doors has a prize behind it. So no matter what you have chosen, I can choose an empty door and I can show it to you. I can show this one. Okay. Now I ask you, do you want to switch? Okay. Do you want to get the other door or do you want to stay with your original door? The answer is yes, I'm pretty sure. Yeah. So here's the thing. What we want to actually answer is, what is the probability that you would win if you switch? And what is the probability that you would win if you don't switch? Right? Now, one intuitive way of looking at this is that, well, one of the doors is going to be eliminated, door number 3 is eliminated. And originally, the probability that 1 had the prize was the same as the probability that 2 had the prize. So it should be the same. It should be 50-50. It shouldn't matter. Okay. But let's again just code this and let's run it and let's see what happens. So this is what I'm going to do. So let's again take some number n, and for n times, let's run this thing. So I'm going to say for I from 0 to n, I want to run the experiment. Okay. Now, how does running the experiment look like? It's something like this. So I'm going to have an array of size 3, which is basically what's behind my doors. Okay. So I don't know, let's just call that door. And one of them is going to have a price. I put that as 1. The other 2 are going to be empty. I'm going to put that, show that as 0. Okay. Now, I said that originally, one of the doors is chosen randomly to have the price. So I mean, in C++, there are many ways to code this. I can do a random shuffle on this array door. Or I could originally just say that all of them are 0, and I just pick a random number and I set that index. Okay. Oh, I have to give a seed to my randomness as well. Okay, so at this point, we have the door. Now, let's say the player chooses a door. Again, the player, let's say, chooses randomly because, I mean, at this point, the player has no idea anyway, so it doesn't matter how the player is choosing. So chooses a random door. Okay. Now, what's going to happen next? The host opens another door. Okay. So how do I open another door as a host? Basically, the idea is that I go over my array of doors, and I want to find the door that doesn't have a price, but is also not the same as the choice. Okay. And I open that. So the remaining choice, let's have something like this. Choice, this is the remaining choice. And the way I find it is like this. I say, go over every door if, okay, no, let's do this open door. I say just go over every door. And if the door is the same as the choice, so if I is the same as the choice, just continue, don't do anything. Otherwise, if it actually has the price, then you also don't want to open it. So if door I is 1, if it has the price, also don't do anything. Otherwise, you open it. So open door becomes I. Okay. Now I have one remaining choice. So I have the remaining choice, which is the door that is not opened and the door that the player did not choose at the beginning. Okay. Again, I'm just going to say for I from 0 to 3, if I is not the original choice and I is not the open door, then the remaining choice becomes I. Okay. I'm trying to code this in a very literal way. I'm not trying to make the code nice. I'm just trying to make it so that you see I'm really simulating the process that I used. Okay. So now at this point, let's say we have two types of players. We have a player who switches, and we have a player who doesn't switch. Okay. So the player who switches would choose the remaining choice, and the player who didn't switch would, of course, have the original choice. Okay. So let's just have a counter. Let's call it player 1 and player 2. Player 1 is the one who's not switching, and I say, so if the door of the original choice is 1, player 1 wins. So P1 is the number of times that player 1 has. And I say, if the door of the remaining choice is 1, then player 2 wins. Okay. And let me also print something. So whenever player 1 wins, I write 1. Whenever player 2 wins, I write 2, just so that we see the result of every experiment. And then in the end, I also write the ratio. So I say, what is the ratio of winnings for player 1? And what is the ratio of winnings for player 2? Mm-hmm. 10. This is 50-50, it seems. Let's do with 100. Suddenly, not 50-50 anymore, it seems. Let's do with 1,000. So you see, as the number of samples is increasing, I'm getting very different results. Okay, let's do with a million. Now, again, by these experiments, I cannot be sure of anything, but my guess at this point is that player 2 wins 2/3 of the time. Okay, let's do 10 million. Did I put one extra zero? I don't know. Okay, we can go back to the video and see how many zeros I put there. Anyway, if we do this a huge number of times, again, it feels like this is converging to 1/3 for player 1 and 2/3 for player 2. But this is not a proof, and there is no way I can be sure of this. I can't even be sure that if I run the same number of experiments again, I would get the same results. Okay. So what's going on here? The problem is that the door that is being opened is not independent of the original choice that you made. Right? So I'm saying that the door that is getting opened is always a door that doesn't have the price. Right? So let's look at this. Suppose that I pick the door, I pick, let's say, door number 2, and suppose that door number 2 had the price. Then each of the other doors would be opened maybe with the same probability 1/2, right? But now, let's say that I chose door number 2 and it didn't have the price. Let's say the price was in door number 1. Then the host would never open door number 1. The host will always open door number 3, right? So which door gets opened is actually dependent on which door I chose in the beginning. And we will see a much better analysis of this very soon. So I'm going to prove to you that the best strategy is to switch. And if you switch, you will win 2/3 of the time. But not now. I'm going to just give you another brain teaser. So this was, I think it's called the Monty Hall problem, something like that. But now I want to give you another problem. This is called the Sleeping Beauty problem. Oops. So here the setting is kind of different. Let's say you're the Sleeping Beauty. And what we're going to do is that today is Monday. No, today is not Monday, but let's say today is Monday, right? And then we're going to have Tuesday and we're going to have Wednesday. So here's what's going to happen. On Monday, I'm going to give you a poison that erases your memory and puts you to sleep. Okay. So you sleep on Monday and then I toss a coin. And let's say this is a fair coin, 50-50 probability of heads or tails. And then if it's heads, I would wake you up on Tuesday. Okay. But when you wake up on Tuesday, you have no memory. All you know is that you have just woken up. You don't know what day it is. You don't know what happened with the coin toss. I mean, even if you had memory, you didn't know that. Okay. If it comes tails, I will wake you up on Tuesday, and then I will give you the drug again. You will go to sleep again, and then I will again wake you up on Wednesday. Okay, and remember the drug erases your memory. So when you wake up on Wednesday, you don't know that it's Wednesday. You just know that you have woken up. Right. Okay, now let's say that every time that you wake up, I ask you, did the coin come up heads or tails? Or let me just put it in a different way. I ask you, what is the probability that the coin result was heads? Okay. What would you answer? Well, one very rational answer is that this is a coin toss. It has nothing to do with the rest of the process. No matter what else you do, it's going to be 50% probability that it was heads and 50% probability that it was tails, right? But let's see what actually happens. So let's see in what proportion of cases when you wake up, the coin toss was heads and in what proportion was it tails. So let's CPP, let's again code this. I'm going to again say that I use my time as the seed for randomness. And let's say I read a number n, and for n times I perform the experiment. Okay. Now, this is my run experiment. And I will keep track of several things. I will keep track of the total number of times that I have woken up. I also keep track of the number of times where I have woken up and it was heads, and the number of times where it was tails. Okay, so every time that I'm running the experiment, this is what's happening. I'm going to say, let's flip the coin. So coin is a random number modulo 2, so that it's 50-50. And let's say that if it's heads, so if coin is 1, let's say 1 is heads, you will wake up only once, so total W increases. And the one time that you wake up, it's because it was heads. Right? I said heads wakes you up once, right? And otherwise, you're going to wake up twice. So total W increases by 2. And total T also increases by 2. Because you're waking up twice. And every time that you're waking up, it's because it was a tails. Okay. So in the end, here's what I'm going to write. I'm going to write, or actually, let me just write heads and tails again. So I write heads here, I write 2 tails here. I'm going to also write the total number of times that we wake up. And I'm also going to write the ratio. So how often was it heads? And how often was it tails? Okay, let's say I do the experiment 10 times. Doesn't give us much information. Let's say I do it 10,000 times. Gives us a little bit more information. Let's say I do it 1 million times. This is very good. Because the first number is getting close to a third. Right? So in some sense, it seems like the probability when you wake up that the coin was heads is only a third. It's not a half. Right? So if you consider all the times that you have woken up, in only a third of them, the coin result was heads. 2/3, the coin result was tails. But this is super stupid because think about what we're saying at this point. We're saying that we flipped a fair coin and the probability that it was heads is only a third. Okay, this doesn't make sense. Now, less intelligent people in philosophy, keep talking about these things. More intelligent people in mathematics and computer science define probability so that we can say this is not actually the probability, right? So we will see that this is not a paradox actually, and it's just because the way we're working with probability is not yet well defined. As soon as I give a good formal definition of probability, this seeming paradox goes away. Okay. One more example, and then I promise you I will do some math. So this is the next example I want to talk to you about. It's a cancer test. So here's the thing. Suppose that I'm a scientist and I have created a great test for a particular type of cancer. And my test is 99% effective in the sense that its result is correct 99% of the time. Okay. So I have this cancer test, and basically what I guarantee is that if you have cancer, the test says yes, or the test says positive in 99% of the cases, with 99% probability. And if you do not have cancer, actually 99 is quite a lot. I think my experiment will take more time than I want, so let's say 90% probability. Okay, and if you do not have cancer, the test says negative, also with 90% probability. So no matter what your condition is, this is a great test. The test is going to give you the correct results 90% of the time. Okay. Now, let's say you take my test and unfortunately it's positive. How unhappy would you be? What is the probability that you actually have cancer? Okay. So you take the test and it's positive. What is the probability that you have cancer?
Depends on like disease rates.
Yes, it depends on what percentage of the population actually do have cancer, which is a bit unintuitive. But let's try to somehow code this one as well, and then we'll see why. So here's the code. We're going to first give a seed to our randomness, and then I'm going to read two numbers, P and C. Basically, P is the population, C is the number of people who have cancer. And then I have a vector up here, which tells me which people have cancer. I'm going to resize it to size P, and I'm going to set it to true for C of the people, and then I'm going to just shuffle it randomly. Okay, and then I'm going to print this, just showing who has cancer and who doesn't have cancer. And then I'm going to read some number n, and I'm going to do the experiment n times. Now, how does my experiment work? Well, I'm going to keep track of two things. I'm going to keep track of the total number of people who have tested positive. And I'm also going to keep track among these people who've tested positive, how many of them had cancer. And I'm going to call that total cancer. So suppose that I am the one who's taking the test. So me is going to be just a random person. So uniformly chosen, random modulo P. And I'm going to have a result. Okay. So my result in the test depends on whether I have cancer or not. If I do have cancer, then the probability that I get a negative result, that I get a result that says I don't have cancer, which I show with 0, is just 1/10. And otherwise, with probability 9/10, 90%, I'm going to get a positive result. And of course, because I have a positive result, I should increase total positive. And because I actually did have cancer, I should increase total cancer. Now, the other case is that I don't have cancer. In this case, with a small probability, with probability 10%, the result is going to still be positive. And in this case, I have to only increase total positive. I don't have to increase total cancer because I don't actually have cancer. Otherwise, the result is going to be C. And then in the end, I'm just going to print the ratio of the total number of cases where it was positive and I actually did have cancer divided by the total number of cases where the test reported positive. Okay, so let's actually compile this and let's see what we get. Okay. So first, let's say I have 10 people and 5 of them have cancer. Okay, and now I'm going to say do 1,000 experiments. So as you see, if the cancer if the cancer test comes out positive, in this case, it seems like there is almost a 90% chance that I did have cancer. So let's increase this. Let's say I have a lot of people, so 1 million people, and let's say half of them have cancer. Okay, this is my sampling. It shows who has cancer and who doesn't. And let's say that now I want to run the experiment also for 1 million times. And as you see, again, the number is close to 90%. But in both of these experiments, exactly half of the people had cancer. Now, let's see what happens if less than half of the people have cancer. So let's say I have 1 million people, and let's say only a very small portion of them, only, let's say 1,000 of them have cancer. Okay? And then I do the experiment again for 1 million times. And in this case, you see that even if the test says positive, the probability that you actually do have cancer is very small. This is a tiny probability. So the actual probability of you having cancer is not only dependent on how good the test is, but also dependent on what proportion of the population has cancer. Now let's do the opposite thing. Let's say that I have 1 million people, and let's say that a lot of them, 800,000 of them, have cancer. Okay, and again, I say do the experiment 1 million times. Now you see that the probability that I have cancer is actually close to 1. It's something close to 97%, it seems. Right? So let's do this again. And let's say I have 1 million people, and but one of them have cancer. Okay. So of course, in this case, you would expect that if your test is positive, there is almost a probability of 1 that you do have cancer, right? And actually, even if you don't consider the test at all, even if you don't take the test in this case, there is already a very high probability that you have cancer because a high proportion of the population has this type of cancer. Now, in this case, it became exactly 1. We will compute the actual probability. It's not exactly 1, but this is, of course, just an experiment. So the experiments are never going to give you the exact probability. So when they tell you that a test is very effective and it works correctly 90% of the time, when you get the result, you might have to take the result very seriously. There are cases where the result is always correct. Or you might just be able to ignore the result completely. There are cases where the result is basically never correct. Again, there is some small error in these things. Okay. So, yeah, we want to formalize all of these things. We want to get to a point where we can talk about everything that is happening here and formally say what we mean by probability, and formally say if I have to take this test seriously, if I have to say here that the probability that it's heads is actually 1/3, which is kind of absurd. And I want to also prove that in this one, the best strategy is to switch. Okay. So now that we've had our fun, let's talk about measured spaces and measures. Okay. So the idea of a measure is very simple. Suppose I have a set and I have subsets of this set. I want to be able to say what is the size, or actually measure is the best word. What is the measure of every subset? So how big is every subset? And when I say how big, I no longer mean it in the sense of cardinality. So for example, if my universe is the set of real numbers, if I give you a segment from A to B, right? So for example, let's say I give you a segment from 2 to 5. And I say, how big is this segment? What is the measure of this segment? What is the length of this segment? Intuitively, you would say 3, right? So it's just that. I want to extend this notion to any kind of set. I want to say that I have a set and I also have a subset. So I have a set of subsets and I'm assigning a measure to each one of them. Now, this measure can be length. It can be in higher dimensions. It can be area, volume, 4D volume, whatever. Maybe my set is not even the set of real numbers. Maybe it's something else, right? So this is what I want. I want to say that, first of all, I'm not going to work with real numbers. I have to just define some small thing here. I define the set of extended real numbers. And extended real numbers means that I have my real numbers, but I also have 2 new elements, infinity and minus infinity. Okay. And they work exactly in the way that you think. So for example, when it comes to order, I can order my set of real numbers in the normal way. And then I say infinity is bigger than all the real numbers. And minus infinity is just an element of the set that is smaller than all the real numbers. And I can also extend my concept of addition. For example, I can say, if I take a real number and I add infinity to it, I will get infinity. If I take a real number and add minus infinity to it, I'll get minus infinity. And I don't add infinity and minus infinity. Okay. So this is extended real numbers, but we're really interested in the positive part of this. So I often talk about positive extended real numbers or extended positive real numbers. And this just means that I have all the numbers. I mean, I said positive, but it's actually non-negative. I have all the numbers in this range, but I also have this infinity itself. So I have all of my positive real numbers, but I also have infinity. Okay. Let's give this set a name. I'm going to call it R bar. Okay. Great. So again, I have a set, let's call it the set A, and I want to assign a measure. So what is a measure? A measure is just going to be a function that maps subsets of my set to values in this set. So it's going to give me a value that says how big this particular subset is. Okay. So let A be a set. And let's say E is a set of subsets of A. So E is a subset of P of A. Okay. A measure, I'm going to call it mu, is a function from E to this set, R bar. Okay. Now, of course, I want my measure to satisfy some basic properties. First of all, one thing you would realize here is that I'm not really assigning a measure to every subset of A. I'm just saying I have a bunch of measurable sets, which I'm showing with E, and I'm going to assign measures only to those. Okay. So first of all, I want to say what's measurable. And then I want to say how this measure works on them. Okay. So here's maybe if I want to put all of these things in the definition together, I say let A be a set, E be a subset of P of A, and let mu be a function from E to the extended real numbers. We say that this whole triple, A, E, and mu, is a measure space if these conditions are satisfied. Okay, so first of all, I'm going to have some conditions on my set E. So what are the subsets that I can measure? Well, I want to, of course, say that I can measure the empty sets. Right. And then whenever I have a condition on E, I'm going to write a corresponding condition here on mu, on how this measure works. So if I want to assign a measure to the empty set, it's very intuitive to say that the measure of the empty set should be 0. Right? Again, we're just extending concepts such as length and area and so on. So if you have an empty set, intuitively, you know that the area is 0. So this is how I'm going to define my measure. I'm going to say, if you call a function a measure function, then mu of the empty set should be 0. Okay. The next thing is that suppose I have assigned a measure to a bunch of sets. And let's say I'm taking the measure of their union. So let's say I have two subsets of A. So let's say X and Y are subsets of A, and both of them are measurable, and their intersection is empty. So X intersection with Y is empty, and both of them are also in E. Okay. Then I want their union to also be in E. So what I'm saying here is, again, imagine the case of real numbers. Let's say I have two disjoint segments. I have a length for each one of them, so I should be able to define the length of their union, right? And of course, the way I'm going to measure it is that the measure assigned to the union of X and Y is just going to be the measure of X plus the measure of Y. Right. But as we've seen with the axiom of union in set theory, this is not very interesting because I'm talking only about two sets. I don't want to talk only about two sets. I want to talk about a set of sets, right? So instead of this, I'm going to actually say, I want to have countable unions. So this is the way I want to write my second one. I want to say, let x1, x2, so on, be a countable set or sequence of disjoint, of pairwise disjoint members of E. Okay. So actually, let me write it like this. Let's say x1, x2, x3, so on. I have this infinite sequence. All of them are members of E. And suppose that they are a countable set of pairwise disjoint sets. Okay. Now, x1 is in E, so x1 is measurable. x2 is in E, so it's measurable, and so on. So I want the union to also be measurable. So I want to say then the union of all xi, so I from 0 to infinity xi, this union is also in my set E. And here what I want to have is that the measure assigned to this union, I started from 1 here. is just the sum of the measures. Again, this is very intuitive. So suppose that, as an example, I have a bunch of segments in R, and all of these segments are disjoint. There's no point that is in all of my segments. And I'm taking the union. What is the length of the union? It's just the sum of the lengths of those segments. So if you think of the normal concept of a measure or a measurable space, or if you think of like areas and volumes or so on, is there any other natural property in areas and volumes that I cannot get as a result of this? I have a problem here, and the problem is this. Suppose that I have a set, and that set is measurable. So I have assigned a measure, for example, to the set from, let's say, to the segment from 0 to 1. Can I also assign a measure to its complement using these axioms? Not necessarily, because I mean, there is nothing here that even says that if a set is in E, if a set is measurable, then its complement should also be measurable. So I want to add that one too. So I want to add this third one, which says that if X is in E, then the complement of X, and of course the complement of X with regards to my original set A. So X complement, which is A minus X, is also E. Okay. But I don't need to have a corresponding condition on the measure. Why? So what is the measure of X complement? So here's the trick. I know that the empty set is there. The empty set is measurable. And whenever a set is measurable, its complement is measurable. So my whole set is also going to be measurable because that's the complement of the empty set. Right? But that means that I have a measure for my whole set. But now if I take a set and its complement, they're disjoint. So the measure of their union should be the sum of their measures. So this means that the measure of the complement is just the measure of the whole set minus the measure of the original set. And I don't have to add this as another axiom here on my function mu. It's just a result of the previous ones. Okay, great. So this is how we define measures. And of course, we have the classical measure on R, also known as the Lebesgue measure. And basically, it says exactly what you would expect it to say. It says that if I have a segment from A to B, the measure is B minus A. Okay, so for every segment from A to B, and honestly, it doesn't also matter if the segment is closed, open, whatever. So for every segment from A to B, the measure is just B minus A. It's the length of the segment. Okay. And then, of course, I'm assigning measures to segments, but I can extend that to countable union of segments. I can take intersections. I can do any set that can be obtained using these axioms, starting with segments. So I know that segments are measurable, and of course, any set that can be obtained using this would also be measurable, and my measure would look like this. So in this case, what is the measure of the whole set R of real numbers? So if I want to find the measure of R, what can I do? I can just write R as the union of a finite number of disjoint segments. Or sorry, not finite, a countable set of disjoint segments, right? So what is R? R is like I can take the segment from, let's say, any number I to I plus 1. Okay, I'm going to have one side, I in Z. Right. This is one way of writing R as a union of disjoint segments. But then the measure of each of these segments is 1. So the measure of R is just the sum of these measures. So that's infinitely many ones. Adding them together, you will get infinite. Okay. Which is, I mean, a very weird way of just saying that the length of the whole real number line is, of course, infinite. Okay. But we're not interested in this exactly. We're not interested in any measure. We are interested in measures that can be thought of as probability. Okay. So I'm going to now define a probability space. And the idea here is this. Instead of just having any set, I'm going to set that and say that this set A is my sample space. So it's the set of all results that can happen in my experiments. Okay. And sometimes people show it with omega. It's too hard for me to write omega. This is hard. So I would just go with S. Okay. So I say let S be a set. And I'm going to call this my sample space. Basically, the idea is that I want to do some experiment, and every time the outcome or the result of the experiment will be a member of S. Okay. And it would be really stupid if S is the empty set. Now, what do I want? I want to say what is the probability that a particular event happens. But what is an event? An event would just be a subset of my sample space. So think of it like this. Think that I have S, and let's say I'm just tossing the coin twice, right? So what are the possible outcomes? What is my sample space? Maybe I get heads both times. Maybe first I get heads, then tails. Maybe I get tails, then heads. Maybe I get tails both times. This is my sample space. All the possible results of my experiments, right? Now, if I want to talk about the probability of something happening, I want to say, for example, what is the probability that I have at least one head? Okay. So when I'm assigning a probability, I'm asking something like this. What is the probability that I either get HH or HT or TH? Right? But what is this thing inside here that I'm assigning a probability to? It's just a subset of my sample space. Okay. So an event has to be a subset of my sample space, and an event is basically what I'm going to assign a probability to. Okay. So I'm going to say, just like before, let E be a subset of P of S. So E subset of P of S. And then I'm going to call this the set of events. Okay. Now, honestly, in most cases, when we're talking about finite or countable sets, I would just take E to be all the subsets. I have this whole game of only taking some of the subsets as events because of the problems with measures. And those problems only happen when you don't have a countable set. Okay. And we'll see that later in this course. Okay, so I have a bunch of events. Now, what are the conditions that I want to be satisfied? Basically, I'm also, again, assigning a measure to every event. I want to say, what is the probability of this particular event, right? So I'm measuring how likely it is that this event happens. Or maybe another way of looking at it is that I'm measuring my belief. I'm saying, how much do I believe that this particular event would happen? Okay. So I will have to have a function P that takes events and maps them to what? I want to get probabilities. I want my probabilities to be between 0 and 1. Okay, so I want to have a function P, or actually I would usually just write it like this in this course to make sure that it's not like this P, it's not the power set, it's a probability. So I have a function, let's say prob, that takes each event and gives me its probability. But the probability of an event has to be between 0 and 1. It also has to be a measure. Okay, so we're working with a special case of a measure space. And this is what I'm going to call a probability space. So we say that this triple S, E, and prob is a probability space if these conditions are satisfied. Okay. So I want my conditions to be basically the same as this. So I want to say that if I assign a probability to a set, I can assign a probability to its complement. I want to say that if I have a bunch of countable sets and they're pairwise disjoint, the probability of their union is the sum of their probabilities. And of course, for the empty set, I want to say its probability is 0. Right? So it's very much like measure. But the big difference is that here I was saying, well, the measure that I'm assigning to the set of all real numbers is going to be infinity. But when I'm working with probabilities, I want to assign measures between 0 and 1. So what should I assign as the probability of my whole set S? Should just assign 1, right? Because if S is the set of all the possible outcomes of my experiment, then the probability that an outcome is in that set should naturally be 1. So we say S, E, and prob is a probability space if, well, E should satisfy all the conditions from before, right? So sometimes they say that E is a sigma algebra. I don't know why they make these weird names. Okay, so basically I want this. I want to say that the empty set is in E and S is also in E. I want to say that the union of a bunch of disjoint subsets of E is in E. Actually, I don't even have to have the disjointness there. I can just say that if x1, x2, so on are a sequence of events, then their union is also an event. The union of xi's from 1 to infinity is also an event. Right? So these are the conditions that I want to have here. And of course, I want to say that it's closed under complementation. So I want to say if X is an event, then X complement, which is S minus X, is also an event. Now you don't need to write all of these things. So for example, if you have the third one, you don't need all of the first one and so on. You can simplify these a little bit. But what's interesting to me is how my probability function works. So the conditions on my probability function would be something like this. I would say that, well, let's say that the probability of my whole set, my whole sample space, and I sometimes write it like this, but now let's just write it as usual. Probability of the whole sample space is 1. Okay. So I want that. What else do I want? I want the condition that if x1, x2, so on are events, let's say are pairwise disjoint events, then the probability that I'm going to assign to their union is just going to be the sum of their probabilities. And yeah, you will get used to this. Sometimes I write P, sometimes I write PR, sometimes I write prob. I'm never going to fix this so you'll get used to me with this. Right. Okay. So these are the properties that I'm going to have. And as soon as I have something like this, I can now talk about the probability of an event. Okay. By the way, I didn't write that the probability of x complement is 1 minus the probability of x. Right? Because I can get that as a theorem, because the probability of S is 1, and X complement are two disjoint sets, and their union is S. So based on this one, the probability of X complement has to be 1 minus probability of X. Okay. So this is how we define the probability space. And now I can finally go back and talk about this one, the Monty Hall problem. Okay. So what is my probability space here? If I want to have a set S of outcomes, well, I can say it's just either 1 or 2 or 3. And when I say 1, it means that the price is behind door 1. When I say 2, it's behind door 2. And when I say 3, it's behind door 3. What are my events? In this case, I mean, I'm working with a finite set. I can say I just let everything be an event. So my set of events is just all of them, every subset. Now, I'm going to have a uniform probability distribution here, which means that every element in my set S has the same probability. This is not something that always happens, but when it happens, it's glorious. So I'm going to say the probability of 1, so the set containing only 1, is a third, which is the same as the probability of the set only containing 2, which is the same as the probability of the set only containing 3. I don't have to define my other probabilities because based on my axioms, they're all defined uniquely now. Because if you have any other subset, it's a finite set. So as long as I know the probability of each of its elements, I can just sum them up. That gives me the probability of that subset. Okay. Great. So now based on this, I want to talk about the concept of conditional probability. So the idea in conditional probability is that I made an observation. And that observation is changing what I know about my experiments. Okay. So in this case, for example, the observation I'm making is that door number 3 is empty. Okay. So let's look at this idea. So suppose that I observe, let's say, some set S prime subset of S. What this means is that I somehow know that the result of my experiment is in S prime. So I have ruled out some of the possibilities. Okay. So let's just copy this again. I have this here. So originally, what are the events that I have? Originally, my events are any subset, right? But suppose that I observe something. Suppose that I observed, for example, that 3 was empty. So now it means that I have a new set, a new sample space S prime, which is only 1 and 2. Okay. So I know that 3 was not the answer. So the answer where the price is going to be either in 1 or 2. So this is what I call an observation. I'm basically making my sample space smaller based on some information. But when I do this, what happens to the probabilities? So do the probabilities remain the same? If I shrink my sample space, I cannot say that my probabilities are again the same. Right? So I cannot say that it's 1/3 probability each, because the probability I'm assigning to the whole sample space has to be 1. And if I just assign 1/3 to each of them, then the sum would be 2/3. So I have to define a new probability space, a new probability function on this new sample space. And this is what I call conditional probability. Okay. So here's the thing. This is my definition. I say, let A and B be two events. Okay. I define the probability of A conditioned on B to mean this. This is going to be the probability of A intersection with B divided by the probability of B. Okay. So the idea is very simple. The idea is that originally I had a sample space and I had a probability assigned to every event, right? But now I'm observing a particular event B. So I know that, or in this case, I just wrote S prime, right? So I know that my outcome is in B. Now I'm asking, given that I know my outcome is in B, what is the probability that my outcome would be in A? Okay. So in this case, I want to somehow scale the probabilities so that the probability of B becomes 1, right? So that's why I'm just taking the probability of the intersection and I'm dividing it by the probability of B. Now we write it like this, but honestly, this notation is not great because it kind of hides what's happening here. What's happening here is that I'm defining a new probability function. I'm basically defining a new probability function. Let's call it PR sub B. And then I'm saying that PR sub B of an event A is the original probability assigned to A intersection B divided by the original probability assigned to B. So this PR is my original probability function. This PR sub B is a new probability function, right? But we write it like this. So you might sometimes think that this is the same function. It's not the same function. It's just bad notation. Okay. So what I'm doing here is that I'm just scaling everything. So let's do this. So in the problem here, if the observation is that door number 3 is not the result, door number 3 does not have the price, my S prime, or okay, let's just call it B, my B here, which is what I observed, is that, well, the outcome is definitely going to be either 1 or 2. Okay. But now what is the probability of 1? The new probability of 1, which is like probability of 1 conditioned on B, is going to be what? It's going to be the original probability of 1 divided by the original probability of B, 1, 2, which is 1/3 over 2/3, which is 1/2. Okay. And similarly, the probability of 2 given B, or okay, I say this, I read this as probability of this one given this one, or conditioned on that one. So probability of 1 given B is 1/2. Probability of 2 given B is also 1/2. Okay. What does this tell you? This tells you that, well, if I had this game, and the game was that, well, I'm putting the prize behind one of the doors uniformly at random. And then if as the host, I just told you the prize is not behind door 3, then with this new information that you have, doors 1 and 2 are equally likely to have the prize. Right? Okay. But doesn't this contradict with what we observed? Because what we observed was that when we were playing, it was always better to switch. Well, you have to be very careful about how you're modeling your knowledge. So in this case, I'm saying that as the host, I just told you that it's not behind door 3, but that's not how the game was played. The way the game was played was that you first chose a door, and then I picked a different door and said that it's not behind that, right? So that's not the same as the probability of this observation. Of course, you're making this observation, but you're making some extra observation as well.